All right, so this is 4.6b. We're going to go through these a little bit faster because you should be better at the fundamental theorem of algebra information as well as the rational roots theorem. So we're going to talk through two other patterns. One you should know, one's a little bit new. So you need to be able to use sum and differences of squares as well as sum and differences of cubes. So we went through the pattern of cubes, so let's talk through the pattern of squares. So one that you should already know is the difference of squares. So the difference of squares says that if you have two square numbers subtracting, that you can factor them out as a plus b, a minus b. Right? And then you can solve it. You have two different values. There's a little bit of why and how and all that good stuff for it. So just in case you weren't sure, if I use this example here of x squared minus 4, and I set it equal to 0, I would have x squared equals positive 4. I would square root that, so x would equal plus or minus the square root of 4, which means x would equal 2 and negative 2. So these two factors here are just a way to shortcut that process. All right, the sum of squares. The sum of squares is a little bit unique because it actually has an imaginary answer, so it uses our I value in there. And it says that if you have two square numbers and they are adding with one another, you can factor them out as a plus bi times a minus bi. So we're going to use that imaginary piece. So if I use this as an example, so x squared plus 4. So 4 is 2 squared, so it'd be x plus 2i, x minus 2i. And just in case to prove that that is true, if we set that equal to 0, so x squared, plus 4 equals 0. And I solved that, x squared equals negative 4, so I would be square rooting negative 4. You should know that I is the value of square root of negative 1. So this actually equals 2i and negative 2i, right? So plus or minus, and then the square root of negative 4 is 2i. So let's try them out. We'll keep that. So if we look at these two down below and you have x squared minus 169, we're going to use the pattern and we're going to solve it just to prove it. All right, so pattern. This is the, since it's subtracting, this is the difference. And 169 is 13 squared. So if I expand that out, I have x squared minus 13 squared, which means I should be able to break it into x minus 13 times x plus 13. All right, so I have x equaling 13 and negative 13. Just to prove it, if you do x squared minus 169 equals 0, we have x squared equals 169. So x equals the positive or negative root of 169. So x equals positive and negative 13. All right, if we have x squared plus 225, adding is the sum. So those are sum of two squares because 225 is 15 squared. So if you use your pattern first, we have x squared plus 15 squared. So it should break into x plus 15i times x minus 15i. Just to make sure, you can set it equal to 0. So x squared plus 225 equals 0. So x squared equals negative 225. And if I square root that, so plus or minus the square root of negative 225. Negative square roots come out with an I, so x is positive or negative 15i. So you should see that same value for them. So you can find your zeros by following the pattern, or you can find your zeros by setting it equal to 0. That's why we call them zeros. All right, fundamental theorem of algebra. You should have talked a little bit about this already with your teachers, but just in case. It's something that's come up before, but we're going to name it now. So using the name, the fundamental theorem of algebra, essentially is telling us that if you look at the highest degree in your function, it also tells you the number of solutions that function will have. So if you have x to the first, you have one solution. If you have x squared, you have two solutions. If you have x cubed, so those are coming from here, you have 3 solutions. Even if it's x cubed and it's extended out, it still has 3 solutions. So let's do these real quick. Determine the number of solutions for the zeros of the function, right? So solutions and zeros, we're asking for the same information, but you name it based on what you're looking for. So if it's equal to 0, you're finding zeros. They're the solutions because if you plug this value in for x, it would output a 0, right? So same information, different name. All right, I'm going to look at it. I'm going to check. Is number 1 in standard form? I see a 5, I see a 2, I see a 1, x to the power of 0. Here is my largest term, so there should be 5 solutions. How about number 2? When you look at number 2, how many solutions should that have? All right, find that 45. It would have 45 solutions. So it would cross the x-axis 45 times. Some of those are probably going to be imaginary, so maybe it won't cross all of those times. All right, look at number 3. How many solutions will it have? Largest degree, so 236 solutions. So that is important because when we finish out a problem and we list out all of our zeros or solutions, we need to know if we did find all of them. So if I did number 1 and I only found 4 solutions, I did something wrong, or maybe I have a double. So it's a way to make sure that you can check that you actually fully